Welcome back to Neural Networks for Architects. This is day 3 on numbers and things. And we want to go into some more complex forms. Imagine the alien sitting at the edge of the world, taking pictures of the world, and you have to do that with numbers. And how to use numbers to picture the reality in good contrast. This is what we want to discuss. And this is very important, because if there's something complicated to understand, it's this. So let's go and look for examples. So in architecture, it's very important that you understand different notions of lines. So they're all the same numbers, but they are thought differently. So what we have is forms, shapes, and continuous forms. Forms are in Renaissance, Euclidean, Cartesian system. So we have, and these are interpolating between 2 points. The points are the numbers you have, and then you interpolate a straight line between 2 points. You can have a series of numbers, and then you get a polygon. So this is always a data, this is a renderer. So in strong contrast to shapes, the same line of numbers, but we are not thinking them as pairwise interpolations. We interpolate the whole thing as a unity. So we think that as a system. So, and therefore the position of each point is not only affecting the neighboring points, so the interpolation here and here, but interpolating the whole line, overall curvature of the line. So this, I would say, is a system. This is always thinking at a unity, not discrete elements, and I would say this is what shapes are about. They are discourses, but I think this distinction between forms and shapes, however it's called, it's very important. In Mathematica, it's done with interpolating polynomial. This is a polynomial. This is how to plot it. An infinite thing is not a graphics, it's a plot. So this, I would say, is a continuous line in contrast to a discrete line. So in contrast to what we have in the 20th century, very prominent is double curved architectures around parametrism today. Again, a list of numbers, but now we are thinking them as a shape or an interpolated line just between these points, then with these points, and then interpolating these 2 shapes towards a line. Therefore, you are again with forms, but not forms interpolating between points, but interpolating between shapes. And this is what we know as Bezier or splines in all our CAD systems. So this is Renaissance Baroque, this is Enlightenment Classicism, this is 20th century on mathematics. It's very important that we see that there is these similar constellation of things, but on another level of abstraction. But these are the three kinds of lines, all with numbers. So now there are some tools with with systems. We discussed functions as a production. Oops. Make it a little bit bigger. So this is a structure assigned here to a symbol with this parameter or variable. If we can say f of 5, then it's calculating, it's producing or predicting a certain result. This is what we discussed. So that's towards the system. Now we can go for the interpolation. This is just the inverse process. You see, we have the x and the x squared. So we have an implicit function This is what we discussed with stochastics, and then we can have an interpolation function, IF, and IF now is able to do the same thing. So get to go for 1.2, and he's able to make a square, even not knowing this, because it assumes that there's a system and we have some points we measured to get the ideal of a system meeting all these points as we had in the continuous lines. So that's important. Now we can go for visualization of these things. Just to give you some indicators, you can go to how this is done. Go for the slider, go for dynamic module to see how this is done. This is a slider, and this produces, the slider produces a number. This number is put into this function, the function produces this value. All this is rendered into this kind of diagram. So just to show you how this is working, a system, the numbers can control all shapes. In this case, we have the parameter x coming from the slider. We put it into the color, we put it to the the rotation, and we put it to the scale. So and then you see what's going on. So it's not only that the shape, I think it's, no, it's by rotation, scaling, and color. So just to see the shape of structures. Or you can, just to show you how this is done, we can take the position of the mouse to control and to run the system shown by this bar. Go here, locator plane, how this is done. Good. This is on systems and shapes. Now this is with images. That's a very interesting line of argumentation. It's an inverse setup like we discussed with audio and sound. So there's a geometry and there's a harmony of images. With geometry we are, so just take an image from the cloud. So this is get some data of this image. Geometry is like the GIF the GIF format, and this corresponds to the RGB. It's in color. The discussion was the same. So these are some information about these vector. The key problem with images and numbers is that they are so extensive. For example, this small image of 220 by 182 has 130,000 dimensions. So it's a vector of 130,000. So if you want to have these numbers here, it's a line of 130,000 numbers. We've seen that we can hear that as noise, and it makes no sense. So it makes sense as this picture if we fold it again. And so if we fold it, so we have to go for the colors. So partition, flatten is flattening it out, partition is making it into chunks. Partition. So now we have to the colors, partition 3, then we have to partition and go for 182. So then we have rendered that as an image. So this is now wrong. We need to partition it into 240. This is just the effect as we had seen with the audio. So this is how numbers and images work with geometry. To put that, make that smaller, this is how it is done. So here, for example, we simply say we want the image resize to 4. This reduces the image to 3 by 4 pixels with 4 colors, and so, which is nothing. Go to 32 and make that, and say image of the result. It's image R. We didn't flatten it, therefore it's still there. Now we get this low-res picture, still 2000 dimensions. If we go to 4, then we have 36 dimensions, and it looks like this. So that's the geometry view to images. And this is what we know with GIF, for example, as a data format in pictures. So, and this corresponds to RGB Newton color scheme, as we discussed. And this corresponds to the waveform of sound. If we look at the waveform of sound, if we go to the frequencies, as we had it with sounds, we can do it with images as well. So, and I will show you how this works. We have the image data of the image, and we go with Fourier on that, which means you look at the image, you look at frequency 1, you look at frequency 2, and take the amplitude of the resonance of frequency 2 for the whole picture, take it out, forget it. Frequency 3, resonance, out. 4, out. So it's about forgetting all the frequencies to the very, to the resolution, which means it's these 240 by 182 in resolution. So these are this is the frequency. There can't be more frequency in here than this. So this is Fourier, forgetting about what is there in space. So this has exactly the same dimension. We can picture that, but that makes no sense. It's like white noise for if we try to see the audio. It simply this is how to hear an image. This is nonsense. So, but this is how to get back to the image, just inverse Fourier, which is just the same like Fourier, and we get the image back, just filling of space with the amplitudes of the resonances. So just projecting it back. So, but we can simply say, and this is what we're doing here, we just want to have the first 6 frequencies. So from 2 to 6, these frequencies. First one is only the, it's a special number, look it up. So therefore, we just have 25 numbers, 5 in X, 5 in Y. So 25 numbers, and these are the amplitudes of the frequencies of the amplitudes of the resonances with these frequencies we took out of the picture, and forget the details. So if we have these 25 numbers, we can project it back to space, just fill the space with that, and this here is just to fill the missing frequencies just with amplitude 0. If we get the image, this is the image. Very interesting in contrast to the resolution here. So this is the view in on numbers in geometry, and this is a view with numbers by harmony. So that's interesting, and it's just inverse to the audio. And it turns out that if you want to have the visual similarities of pictures, it's much more powerful if you use these numbers instead of these numbers. So therefore it's so important to look which kind of numbers and which kind of calculation you're using. So there's an interactive version to see how this, because it's good to get a feeling of how this works, how to, if you fill a space with frequencies. So you see, this is just frequency 2. It's just 4 numbers. And here you're adding more and more. And now you see, it's complicated to get a sharp edge. But here you're there. And this is very few numbers. Let's look. Just 30. And you're very precise. This is what JPEG is doing. Good. Having that, we can do the same, astonishingly, interestingly, with sketches. So what we have here, again, this is with Fourier. What we're doing here is, if a sketch has a certain point, then we don't look at it as x and y in Euclidean. We simply say this is the amplitude of a frequency. So then we say it's x and it's rotation, and by that we put it like, we read the picture as as these frequencies we've seen with the audio. This is done with a complex number, and then we put a Fourier on that to get the frequencies. And then we are able to do this is here, this is again a high-pass filter as we did with the picture, and then we are able to get it back and forth, and there we are. So this is what these functions are doing. Now let's go with some points and create a graphic. This graphic gets these points. Here we subdivide all these points here with a resolution of, I think, 8 intermediate points on these lines to get enough points for the frequencies. And now looks what's going on with this thing here. So now we have a high-pass filter just on frequency 3. And if we go, it's coming. It's the same like with the pictures, just with the line. So to read the y as with the complex here, to read the x as a real and the y as a circular axis. This is what the complex numbers are. We are like these frequencies on sound. So we look at it as sound, and then we can go with the harmony with Fourier towards the frequencies, and then we have a harmonic view to the shape of things. And this is more impressive if we go then to a sketch. For example, here with the mouse, a cat. We have this cat. This gets for the contours of the cat. LNS, it's just these numbers, and we can say graphics of LNS, line of LNS, and you have the cat as a line. So, and this now uses LNS, it's dynamic, and now you see it goes towards the cat. So it's very important to get an understanding what complex numbers are, what rotation, what linear is, what the frequencies are, and so on, just to play around with these things. Good. That's with shapes. Another problem is, or another way to do it here. For example, if you have rooms in architecture and you want to make a vector for that, neural networks always need a constant. In most cases, there are certain algorithms just, for example, for time series prediction, then it's different, but they need always, for all elements you're working with and all the examples you're working with, you want to train with, they need a constant vector. So, but your rooms are polygons of n edges. So it can be 6, there can be 4, it can be 12, and so on. You have no control of that, and you need a single vector for that. Again, you simply circle that, you get the distances, and this is a vector of 25 here, of 25 length of points, and that's it. To measure a polygon of any size. So, and imagine, it's very important. Numbers always circle things as a unity. So this is a kind of number because it's circling. So taking pictures of a graphics, again, if you have a graphics, and if you want whatever, it's getting complicated and you have too much details and so on, not a bad idea just to take a picture and treat it as a picture, because there the vector is constant. This is done with rasterize, and here is raster size. So, and that's the vector. And then you can treat it as an image, make the compression, go with Fourier for the harmony and so on. And this is an example for where you have very complex graphics and just take a picture of it. So this is geographics, you can look it up, how this works. This is the center of Zürich. It's OpenStreetMap, and then you make an image of 128 of it, and then you can treat it as an image, which means you get very urban, developed environments as similar points of this planet, just by taking the image and comparing colors and distribution of colors. So that's with graphics. This is another example. Sometimes you want to characterize an image just by certain elements. In this case, for example, just count the points, corner points. You don't want to have the picture at all, but just these kind of elements. So there's a huge bunch of different analysis of functions for analysis of images available in Mathematica. This is one of it. Keep that in mind, that you're not helpless. So you have very specific instruments to measure and to take numbers. What is super interesting is what we have with key points on images. So take a picture. Again, our Betty of Gerd Richter. And now Mathematica is providing that you find here, in this case with the method serve, there are others, 12 of these features and key points. To show, it's like, you can do it like this. So this means there are very characteristic, distinct flows of colors. So they are characteristic. So, and he finds 12 of these. You can have more, but take that. But these 12 are constant, independent of pictures, and you simply, and they are very characteristic. Imagine this is much better than just the 12 pixels we had with a very low dimensional GIF of Betty. So, and these points here, we have it here. Let's, for example, go with point 1. Points 1. So these are all the numbers we get, and we get it and these are very, so if we go here for its position, orientation, scale, contrast, the descriptor, then we are with 6, So this is the descriptor. No. This is 0.6. So we want to have 1.6. So this is a descriptor. And this is some 40 dimensions. But these 40 dimensions, let's say that it's rotation invariant, and it's characteristic for this flow of colors. And you find it in all the pictures. So this is, again, a certain space of characteristics within pictures. And you can compare. So therefore, we can make a kind of alphabet or a bag of things within pictures. And this is, then you say, this is, for example, A, B, F, G. So A, B, F, F, G, and another G. So, and by that you can get characteristic words for a picture, representing a picture very precisely and fast and compact. So it's another way how to do things. So, just as an example, how to think of it. Or you can use very simple. You can use existing neural networks. There is super complicated. So, but they are already trained. So with millions of pictures, and they give you some vector as result. So let's check what they're doing. Take our picture and make it upright. So this is again this, and ask our network what this is, what the network has to say. That's a book jacket. That's interesting. It doesn't recognize it because it's distortion, and very uncharacteristic. Very characteristic with this painting of Richter. That's interesting. If you want to get more interesting things, so you simply don't care what this network really does. You just want to get a certain discretization and a certain perspective to your images you want to work on. Just take it as it is. Don't take it so too serious. But for example, here. You see, there's hairspray, there's a t-shirt, there's a comic book, a booty, a seatbelt, perfume, wig, sunscreen, hairdryer. It's not too bad as a characteristic of what's going on in this picture. If you have only 1,000, and like in this case, 1,000 objects to detect. So, but now we can go. If we want to work with it, we don't want to have this result. Just to show you and get you an idea, we will go in depth in our next days. So you see, complicated network. We just want to have this 1,000-dimensional vector here, and the linear vector here. So therefore, we can say, copy this. We take the first to the but last. And then we have the linear layer here and the 1,000-dimensional output, which means we can do with NM2 on image. And then we get a 1,000-dimensional vector, which is very discrete, and so very specific to what we see, and somehow reflects what's going on here, and you can work with it and make your own stuff with it. So, for example, get here these images. We have here cats and dogs. Now we can go and make our within these 1,000-dimensional space of our things we want to distinguish. Take this and reduce this dimension to 3. Dimensionality reduction to 3. Oops. This just delivers a new input line. So this is not an output, it delivers an input line. So I have to deliver this, and then it's running. Now we get a dimensionality reduction. This takes a little. Okay, which now means if I go with the dock, he first gets the 1000 of this dock and then reduces it to 3. So we have a 3-dimensional vector characterizing the dock with the power of making differences of this huge network we just took. So now it's a point here, and then you can ask for the Euclidean distance of these two docks. Just look of these two docks. Go here, copy. I think it's not good. Copy and paste this. The big things is you take a Euclidean distance of dr of nm2 of this dock, and take for example this dock. So, and visually it's very distinct. It's very distinct, and we have a distance in this 3-dimensional space of 17, so it's visually very distinct. So if we now go here and take a cat, which is it's this distance. This is visually similar, and if you make this, we get a much higher distance because semantically they are different, because this is a cat and this is a dog. This is a dog and this is a dog, therefore they are similar. So when we made it just by pirating or using a pre-trained network. So I think that's it with our episodes on how the aliens sitting at the edge of the world taking pictures in smart ways. Thanks for watching. The next will be on large set of numbers. So you need always tens of thousands, 100,000, millions of pictures, as we've seen here, for example, with this network, or with our text environment, 5 billion words of Wikipedia, just to make a lexicon of words. If you want to manage that, you need some tricks. And I give you an introduction with the next chapter. Thank you for watching. Seeing you soon.